Good morning, students. Today I am taking one more topic from the chapter Real Numbers, and the topic name is the topic concept is theoretical concept about the topic is let P be a prime and A be a positive integer. P be a prime number and A be a positive integer, such that P divides A square. This is given. If P divides A square, then P divides A. This is the theoretical concept about a prime number and a given positive integer. If P is a prime and A be a positive integer, then and P divides A square, then P divides A. So I am taking one problem based on this theoretical concept. Prove that under root 2 is irrational. We are well aware about the rational and irrational numbers. All those numbers, they can be expressed in the form of P upon Q, where P and Q are some positive integers, some integers, and Q not equal to 0. But those numbers which are not rational are called irrational. So we have no theoretical concept about irrational. Those numbers which are not rational are called rational. So we start with that. Suppose under root 2 is rational. If we prove that root 2 is not rational, then it is clear, it will be clear that root 2 will be irrational. So now start with, suppose root 2 is rational, then there exists co-prime. Co-prime means those integers whose SCR is 1. That means two integers, they have no common factor other than 1. P and Q, such that under root 2 equal to P upon Q. Because if root 2 is rational, then root 2 can be expressed P upon Q. Cross multiply here. So we have P equal to Q under root 2, square both side. So now we have P square equal to 2Q square. Now this is the multiple. Q square is in the form of multiple of 2. That means this number is clearly divisible by 2. Okay? So this number is divisible by 2, so also P square also divisible by 2. So 2 divides P square. Now we use this theorem, theoretical concept. If P divides A square, then P divides A. So here 2 divides P square according to this. This means 2 divides P according to this. Let if 2 divides P, that means P is in the form of multiple of 2. So we can write it P equal to 2m for some integers. P equal to 2m, put in equation first. We have 2m whole square equal to 2q square, 4m square equal to 2q square, q square equal to 2m square. This again shows that this particular number is divisible by 2. So q square also divisible by 2. So 2 divides q square, that means 2 divides q. So this there are 2 steps are there. Since 2 divides P and 2 divides Q, this implies that 2 is common in P and Q. This implies that P and Q are not co-prime. This is contrary of our assumption that root 2 is rational and P and Q are co-prime. This is contrary, so root 2 is irrational. Because we start with root 2 is rational and there exists co-prime P and Q. But this is the contradiction of our assumption that P and Q are co-prime. So if P and Q are not co-prime, that means root 2 is not rational, that means root 2 is irrational. This is a problem, one problem based on this theoretical concept. Now I am taking one more problem based on the theoretical concept. If a prime number divides of any given square of any positive integer, then this particular prime number divides also a given number. So now we want to prove here under root 5 is irrational. So we start again with the contrary, let under root 5 is rational. Square root of 5 is rational. Then if root 5 is rational, then there exists co-prime P and Q. Co-prime means having only a safe one and no numbers is there is equal to 0. Then under root 5 can be expressed in the form of P upon Q, taking cross multiplication. So P equal to Q under root 5. Squaring both sides, we have P square equal to 5Q square. This way of writing is showing that 5 divides 5Q square. So we can write it from first 5 divides P square. That means 5 divides P. As per the concept of theorem, if any number divides P square, then it is also divides P. So we can write it P equal to 5. Put in equation first 5m square equal to 5q square, that means 25m square equal to 5q square, that means q square equal to 5m square. So 5 divides q square, that means 5 divides q. Now we have 5 divides q, here we have 5 divides p. 5 divides p and 5 divides q, and we choose here p and q as a co-prime number, since p and q both divisible by 5. This implies that p and q are not co-prime. This is contradiction of our assumption. So under root 5 is irrational. So this is one more problem in which we want to show that under root 5 is irrational. We were aware about the definition of rational number. Each rational number can be expressed in the form of p upon q, where p and q are some integers and q not equal to 0. So we will start with the contrary, because we have no special definition for irrational. We only know that if any number is not rational, it will be irrational. So we prove here under root 5 is not rational. But we start with contrary, that under root 5 is rational. Then there exists co-prime p and q. That means only common factor is 1. can we express under root 5 equal to p upon q? That means p equal to q under root 5, p square equal to 5q square. This way of writing shows that 5 divides 5q square, that means 5 also divides p square. So 5 divides p square, 5 divides p according to the conceptual theoretical concept of the theorem. So now we can write it, if 5 divides p, then p can be expressed as the multiple of 5, so p equal to 5m for some integer m. Put in equation 5m square equal to 5q square, break the whole square, we have 25, m square equal to 5q square, so q square equal to 5m square. This shows that again 5m square is a multiple of 5, so q square is also multiple of 5. So 5 divides q square, 5 divides q. So these two steps showing that 5 divides p, 5 divides q, that means p and q both divisible by 5. So this shows that p and q are not co-prime. This is the contradiction of our assumption that p and q are co-prime. That means our assumption is wrong. Root 2 5 is rational, root 2 5 is irrational. Thank you. Now I am taking one more problem. Prove that 3 plus 2 under root 5 is irrational. Let us assume 3 plus 2 plus 5, 3 plus 2 under root 5 is rational. This is the contrary of our statement. We want to prove here 3 plus 2 under root 5 is rational, but we have no particular definition for rational numbers, so we have to start with the assuming that 3 plus 2 under root 5 is rational. Then there exist co-primes p and q such that p upon q equal to 3 plus 2 under root 5. If 3 plus 2 under root 5 is rational, then this can be expressed in the form of p upon q, where q and p are some integers and q not equal to 0. This can be written as p upon q minus 3 equal to 2 square root of 5. Take LCM in left hand side, so we have p minus 3q upon q equal to 2 square root of 5. In next step we have p minus 3q upon 2q equal to square root of 5. In left hand side given value is rational. Why? P and q both are integers, so difference of two integers also integer. 2q, q is an integer, so 2q also integer. The different ratio of two integers is known as the rational number. And right hand side is irrational. We have already proved under root 5 is an irrational number. This is not possible. According to the condition of equation, left hand side is rational, never be rational, and right hand side never be rational. Two different numbers cannot be said equal. This implies that so our assumption is wrong. This implies that 3 plus 2 under root 5 is irrational. So these are some examples based on The theory: if any prime number divide the square of any positive integer, then this prime number also divide the positive integer. Thank you. Now I am taking one more problem based on the theoretical concept that if any prime numbers divide the square of any positive integer, then this prime number also divide the given positive number. So the problem is that prove that under root 2 plus under root 3 is irrational. Let us start with this. Let us assume under root 2 plus under root 3 is rational. Then there exist co-prime P and Q such that P upon Q equal to under root 2 plus under root 3. This implies that P upon Q minus under root 3 equal to under root 2. Squaring both sides. Now here P upon Q equal to under root 2 plus under root 3, because we are assuming here root 2 plus root 3 is rational number and each rational number can be expressed in the form of P upon Q. So now squaring both sides, we have P upon Q minus under root 3 whole square equal to root 2 square. 3 square plus 3 minus 2P under root 3 upon Q equal to 2. This whole square open by the a minus b whole square, a square plus b square minus 2ab. In next step, now we have p square upon q square plus 3 minus 2 equal to 2p under root 3 upon q. P square upon q square plus 3 minus 2 equal to 2p under root 3 upon q. Again, p square upon q square plus 1 equal to 2p under root 3 upon q. This implies that p square plus q square upon q square equal to 2p under root 3 upon q. This implies that p square plus q square upon 2pq equal to under root 3. Q is cancelled out by q, 1 power of q. So now we have p square plus q square, 2p comes here, 2pq is equal to root 3. In this equation, clearly observing here, left hand side is rational and right hand side is irrational. P and Q are primes or integers. So square, sum of the squares of primes of integers is always an integer. Product of two integers always an integers. So this is the ratio of two integers in the form of rational number. This is already we proved earlier in previous question. So this is not possible. What is not possible? That is, this is the equation. Left hand side is rational and right hand side is rational. This type of condition is not valid for the equation. This implies that our assumption is wrong So this implies that under root 2 plus under root 3 is divisible. So these are some problems based on the concept that if prime p divides a square, that means p divides a. So this is a theoretical concept. If prime p divides a square, then p also divided. These are the problems based on this type of theoretical concept. Thank you.